So Josip comes from GTH3. He's going to talk about learning implicit generative models using differentiable graph tests. Sorry for the quality. I guess it's fine. Okay, so I'm Josip, and this is a joint work with my advisor, Josip. So what I will talk about is about the differentiable two-sample test that we have developed and how you can use it to learn implicit models. So the test that we want to solve is basically we want to fit a very complex distribution for which we do not have a good parametric family that we can fit. So what we do is we're going to fit an implicit model. So what is an implicit model? Those are the family of models that you can sample from, but you cannot evaluate their distribution, their density. So what we do is you take a known measure, let's say you sample from a Gaussian, then you send your Gaussian to a neural net, and then on the other end of the neural net you're going to get these transform samples which you would like to resemble the original distribution. So the main problem is, of course, how do you devise a loss function so that you can tune this neural net to have samples that look like the distribution you're trying to approximate. So one way to go about this is as follows. So first you sample n samples from your noise, so from a normal. You send it to a neural net F, and on the other hand, you're going to get your n samples from your proposal distribution Q. Then you sample also, let's say, n samples from the distribution you're trying to approximate, that is from P. And then you put these two samples in front of a judge, which is a two-sample statistical test. So these tests are designed to differentiate between the scenarios where the two samples come from the same distribution and they come from different distributions. So the statistical test is going to give you a p-value. If the p-value is lower than some threshold, let's say 0.05, you're going to reject the null hypothesis that it comes from the same distribution. So then the basic idea is pretty simple. You're going to optimize F, that is, you're going to optimize the neural net so that to fool the test. That is, you want the test to produce high p-values, so you cannot differentiate P from Q. And first the idea was designed for MND in 2015. So the family of tests that we consider are called graph tests, and they're pretty simple to describe. So you basically have to follow these 5 steps. So first what you do is you take the samples together, which we colored here green and blue, and you pull them together. So once you have pulled them together, you will create a weighted graph on the pulled sample. And for example, as ways you can use any arbitrary function, but typically what you do is you use, say, the Euclidean distance between them. So once we have this weighted graph, what you want to do is you want to extract a subset of the edges that define some neighborhood structure, okay? So what they did here, they connected every node to its closest nearest neighbor, okay? And these are the set of edges that we select, and this we call U. So the intuition behind the test goes as follows. So basically, if the two samples, if the two samples came from the same distribution, then if you take a look at the kind of edges, right? Because now you have edges that are blue, 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 green, and green, green. Then you can compute an expectation of how many of these things you should be getting, right? So that's why in the fourth step, what you do is you're going to compute the number of edges that cross. So edges crossing if it connects basically two nodes that have a different color, okay? So now, let's say you got this number 7, but how do you know if 7 is a critical number or just you got it by random chance? So what you do is you're going to perform a permutation test. So the idea is that the data is exchangeable. So what you can do is you can just reshuffle the colors of the nodes if P and Q were equal, and in which case you get exact draws from the null distribution. And then basically you simply compute your percentile under that distribution. So to implement this, what you're going to do, you're going to sample once, you're going to sample once again, you're going to sample once again, and every time you sample, you're going to record how many crossing edges you got, and then you compare this to basically the original statistic that you got. So it's pretty simple to implement, and what they have just described, when you connect every node to its, in that case 1, but in general to its k nearest neighbors. So this is known as the k nearest neighbor test, and it has very nice statistical properties. It has been analyzed in the 80s, and what we know is that this is asymptotically consistent. and moreover, if you, its statistic converges almost surely to specific F divergence between P and Q, okay? Another test which we also analyzed is called the Friedman-Rovsky test, and this is kind of a multivariate extension of the runs, of the one-dimensional Bolt runs test. And instead of constructing the one nearest neighbor graph, you construct the minimum spanning tree on the pooled sample. This is known to be asymptotically consistent as well, and you also have a convergence to an F divergence. Also, the tests seem pretty similar because if you plot the F divergences to which they converge, they look very similar to one another. So you have basically this quadratic behavior around 1, and then they grow linearly, the penalty grows, the F grows linearly as P and Q become further from one another. Okay, so not just that they're asymptotically consistent, but they also are non-parametric estimators of a specific F divergence between P and Q. So why we cannot plug this in your favorite, let's say, in PyTorch in your favorite automatic differentiation software to be able to devise a loss function? The main problem is that these tests are not differentiable, so you cannot easily use a first order method. Specifically, let's see how they're constructed, so we can also analyze how to get a remedy or how to get a way around this. Okay, so as I said, so use the set of no edges that you connect. And to get U, what you do is you essentially solve an optimization test, right? You say, among all the edges, among all the subsets U of edges, where a capital E is the set of all edges, you want that subset whose sum of weights is minimal, okay? But you also want to satisfy some constraint, which we here wrote in a very generic form, nu of U, where nu is basically a function that's 0, 1 valued, has to be 1, okay? So this is a very simple way of writing U has to satisfy some specific constraints. For example, in the k nearest neighbor case, what you want is you want every node to have exactly k incoming edges, or in the Friedman-Rovsky test, you want, if you take U, that should be a spanning tree. Okay? So this is of course not differentiable, and the statistic, which is the number of edges that cross in U star, is also not differentiable. So instead what we do, we say we will not commit to a single U star, instead we're going to define a distribution over the U's. Okay? So we took maybe the simplest distribution you can come up with. So given the setting, so we took the objective value, put a minus in front, and exponentiated it. Okay. Then there's this lambda, which I'm gonna talk in a bit, which basically is a temperature parameter. And then we put nu of U outside because we want the distribution to give a probability of 0 if the constraint is violated. So then the statistic becomes, instead of the number of crossing edges, we use the number of crossing edges in expectation. So this turns out to be differentiable, and we also have asymptotic normality of the statistic under the permutation law. Okay? So the observation that we make then, so thanks to the classical properties of exponential families, so to compute the statistic, to do the forward pass, you need the first order moments under U, under P of U, and to do the backwards pass, you're going to need the second order moments. So basically, to apply this framework, you have to know to do inference in the discrete model P of U. So before I tell you how to do that, let's focus on the effect of lambda. So lambda is called the temperature, and as lambda goes to 0, you're going to get exactly the map solution, which is the minimum spanning tree, right? And then if you start increasing lambda, the mass is going to start to spread out across the other edges, okay? And this is what I'm plotting here. So the thickness of the edge is the marginal probability of that edge, okay? So if you look closely, there are some scenarios where you have 2 points where basically the nearest neighbor is, for example, choice is very close to a tie break. But thanks to this, the mass is going to get distributed when you have things which are close to a tie break, the mass is going to get distributed across the edges, okay? So one way to think about this is instead of using the map estimate, we can also take into consideration the uncertainty around the map estimate in the statistic. So, of course, the main question is how do you compute these things? So, I'm going to tell you about the k nearest neighbor, how to compute it, and for the Friedman-Rovsky test, we can also do it, but we do not have time for the talk, so please come our poster. So, when you have the k nearest neighbor test, what is important is that all the nodes are going to be independent from one another, because the constraint is going to separate across the nodes. You're going to have for every node, the number of incoming edges has to be exactly k. So this turns out to be known how to do inferencing. It's called a cardinality potential, and you can compute it in time nk using the very clever algorithm of tolerance squared. So to get a feeling of how it works, let's consider the one nearest neighbor case. In the one nearest neighbor case, you're doing the following. You have your graph, and then you take any node and you compute a softmax over the edges that connect that node to the other nodes. And then in the objective, what you want is you want the output of the softmax and the positions that connect that node to nodes of a different color to be large. Okay, so it's pretty easy to implement. It has a few lines of code. And it's, for those of you that might have noticed, this is very related to neighborhood component analysis, which is used to learn embeddings. So the Friedman-Rofsky test, it's more complicated, but you can also do it in cubic time if you do it naively, or in square time if you use a fast Laplacian solver. So the first experiment that we did, we do power analysis. So we are in H1, that is H0 does not hold. We're in a setting where we take two Gaussians. So the first Gaussian is normal, zero identity, and the second Gaussian is zero identity, but we change the first coordinate of the variance to 3. So while this problem is pretty simple, when you have low dimensions, it gets pretty complicated as you have higher dimension. So what I'm plotting here is the power of the test as a function of the dimension. So this is the classical test, and as one would expect, the power goes down with the dimension. So then what I'm going to plot now, so these are different, so this is a smoothed version under different temperatures. And as it turns out, if you keep the temperature pretty much constant with the dimension, it turns out that this test has a much higher power. Okay, so compare here the purple line with the red line at the very top. So the increase in power can be pretty big. What we then did, we analyzed two specific scenarios. For two specific scenarios where we did the same experiment with different number of samples, and we found the same behavior. The smoothing can significantly increase the smoothing of the test, which to us was a bit also surprising because we were looking into this kind of test for inference and not for statistical testing, for learning models and not for statistical testing. Then we also compared with some classical tests like the energy test or the MND test, which is pretty well known, and it turns out that for these specific alternatives, we have a much higher power. Then we did a very simple toe experiment. So in the toe experiment, we have this weird distribution that we're trying to fit, and then we analyze what the behavior of the temperature and the fit. So it turns out that you would probably like a lower temperature, and it's not that the distribution looks nicer, but also if you have a look at the test statistic, it's very close to normality. So what I'm plotting here on the second row is the true p-value versus the estimated p-value, and then we see that the estimated p-value is under normal approximation, and what you see that the line gets closer to y equals x, which means that the test becomes closer to normality. Then we also did experiments on MNIST, so we tried both the one nearest neighbor, which is very easy to implement and can run fully on the GPU, and also we did Friedman-Rofsky, which can also run on the GPU if you can solve linear systems on your GPU. And we found out that so this is without a lot of tuning, and we found out that the samples look very similar to what you would get, for example, from MMD. So if you'd like to find out more, please come by our poster. We have interesting things. For example, the Friedman-Rofsky test turns out they have very nice connections to spectral sparsifiers. And we also released a PyTorch implementation of this test, but also of MMD, energy tests, and some other things which you might find useful. So thanks a lot.
So we have time for one question.
Thank you very much for the nice work and presentation. I have one question. So, from working with MMD, it's clear that the space that you define your kernel on is really relevant. And in high-dimensional things like images, say 100 by 100 image, it becomes really challenging to define a useful ground metric to define a kernel. So do you think your approach can be extended to also learn the embedding space you run your spending tree on? For example, the work from Generative has done this for weighting, at least as I mentioned in the MMD case.
I see, so somehow min-max where the max goes over the embedding. So I tried this in a very simple, I also tried this in a very simple setting and I couldn't get it to work. And I think if you use it as a general mapping function, I think we have to be careful how to choose the mapping function. I think the same result was also for MMD. If you just use a general mapping function, you would try to do kind of a min-max of MMD gain. For an MMD gain, you're going to have a problem, I think. So I'm not sure what's the right set of functions to consider, but maybe it's going to be less prone to the choice of the mapping. So I'm not really sure. Thanks.
Okay, thanks for the figure.